Hello, my name is Greg Belgrad, and this is a video for the Test 1 wrapper for Physics 2212 Modern section. And the point of test wrappers is to pick a question, go through that question step by step, and try to create a tutorial that will help some students better learn their mistakes on tests, which will better prepare them for the final exam, future questions, etc. So this problem is problem number 4 from test 1, which gave a lot of kids trouble, including myself. But I went over it, went over the solution key, and I designed my own solution that will hopefully better help those who need better explanation of how to solve this problem. So problem number 4 begins like this. Consider a thin plastic rod bent into a semicircular arc of radius r with the center at the origin as shown in the diagram. This is the diagram. The rod carries a uniformly distributed positive charge plus q. So here's my diagram. See, the rod is bent. You have your differentials, d theta, dq. You have your charge, and then we go into the first part of this problem. Determine the electric field dE at the origin due to the representative piece of rod dq. Your answer should be a vector and given in terms of d theta. So this problem statement gives you hints already. So dE, there's a formula for dE that you can essentially just plug and chug. And vector, that's a very another important piece of information because your final answer should be a vector. So you should set up the problem and work through the problem, keeping in mind that there's a vector in there, but also try to adapt your problem to suit a vector. And then d theta, which is your differential, meaning there's probably going to be an integral in there somewhere, or at least if later in the problem, try to tailor whatever you're going to integrate later into terms of d theta. So when you're dealing with vector problems, what you first want to do is you want to find your vectors and your unit vectors and etc. So here's the actual vector. So it's the observation location minus the original. So the observation location in this case is the origin, which is there, and then negative r sine theta, r cosine theta, etc. So that's your sine, that's your cosine. So in this case, your sine is your x vector and your cosine is your y vector. But that will play very handily later when we do our integration. So then you find your vector, which is r sine theta, negative r cosine theta. You can find your magnitude, which is just r. And then you can find your unit vector just by dividing these two pieces of the vector by the magnitude. So you get sine theta and negative cosine theta and 0. So you move into the actual formula for dE. So here's their given formula, 1 over 4 pi e naught dq over r squared times the unit vector. So we had to figure out what is dq. So here's dq, which is equal to lambda r d theta. And lambda is equal to this quantity q over pi r. So these r's cancel, leaving us with q over pi d theta. Then you can plug this quantity back into here, starting with the original formula. Starting with the original formula, and then you can plug it back in here. And your final answer is when you do all the factoring. So here are all your constants. You can even move this under here, but I just decided to leave it as d theta over r squared anyway. So you're left with q over 4 pi squared e naught d theta over r squared times your unit vector. So we move on to the second part after solving for dE. So now it's calculate the electric field E at the origin due to the entire semicircular rod. Your answer should also be a vector. So we found our dE. So when we want to find E, we have to integrate this. We have to integrate this term. So we're integrating from 0 to pi, and the axes are slightly shifted, but it doesn't really matter because you can still do it anyway. So you're integrating from 0 to pi, and you have your dE, and you have to integrate. This whole vector. So you can take out all your constants, q over 4 pi squared e naught r squared, and then you integrate this whole vector. So once you integrate it, the integral of sine is negative cosine, and the integral cosine is negative sine. So and you have your values. So the integral of negative cosine is negative sine, and that will just cancel out and give you 0. And for negative cosine, when you plug in these two values, will give you a 2. So then your electric field would kind of equal this. So your electric field is equal to q over 2 pi squared e0 or e naught r squared times unit vector 1, 0, 0. So, but you can also, like, this makes sense conceptually. and we'll go back to the diagram. So when you have an electric rod, when you have a rod with an electric charge Q, and you're somewhere along in this area, what we learned previously was in spheres that are shells, inside that sphere the electric field is equal to 0. So you could ignore this line and just treat it as almost like you treat it as a hemisphere. So when you're looking at your y's, no matter where you are, your y terms are always going to cancel out. But your x terms, given that it's symmetrical on the y side but not on the x side, your y side will cancel out. But your x side will go over this, because for notation purposes, your plus q will always have an electric field pointing outwards. So when you look back at your final answer, q over 2 pi squared e naught r squared times unit vector 1, 0, 0, that unit vector is going to the positive x-axis. So the numbers make sense, and the conceptual evidence backs up that answer. So now we move on to the second part of this problem. So it states that now consider an additional thin plastic rod bent into a semicircular arc of radius r with center at the origin as shown in the diagram. This rod carries a uniformly distributed charge of negative q. Together, these rods bend to form a perfect circle. So there's our diagram. I drew the lines in the circle and afterwards, but after I explain it, you'll see why later. So this is part C. So what is the direction of the electric field at location 0, 0, L, where L is greater than the radius of the rod, or of the circle? Briefly explain how you determine this. Hint, consider how this object would appear far away. So that is a very big hint. So imagine L is very, very big. You're at a very, very far distance away on the z-axis. So you're looking at it head on. So imagine you're looking at this very, very far away. I'm zooming out for effect. So it is in the 1, 0, 0 direction. So that electric field would be in the positive x direction. And far away, the object resembles a dipole, so a point charge. So treat that dipole as a point charge. And the location 0, 0, L is perpendicular to the dipole axis. So you're looking at this head-on. So imagine the length of this pen is L, and it's pointing out of the page. So when I did this, imagine me at the top of this pen. So I'm looking at this side of the circle and that side of the circle. So the electric field, so for notation purposes, Q is always pointing out, and negative is always pointing in. So when you add up all the vectors, so Q should be going like this, and negative Q should be going like that. There's your Z component should cancel, your Y component shouldn't equal anything, but your X components should add together to form a positive X. So when you add up all your vectors, it'll be pointing in the positive X direction. So that's how you can do conceptually, but this is also, essentially the same answer. So that is how you solve this problem. I hope this helped, and I want to wish everyone good luck for our next exam. So study hard.